second session of the CCAM webinar series, The Importance of Being H.P.C. Earnest. It is a series motivated by the impact that H.P.C. has on simulation and modeling. In this series, we invite leaders of collective initiatives, projects, institutes in Europe and the USA which focus on the challenges of the development of scientific codes, algorithms, and data-driven initiatives in the context of the coming H.P.C. landscape. We organize these webinars in the CCAM spirit, and we bring together complementary initiatives that focus on the science that is made possible by combining modeling methods with the optimal exploitation of H.P.C. resources. We aim at fostering an open, informal dialogue, also as interdisciplinary as possible, and that's why in each session we invite initiatives that cover different areas that are of interest to the Greek CCAM community. So these sessions are chaired by Sara Bonella, and the CCAM Deputy Director, and myself, and they are organized by 3 presentations that will go one after the other, and then at the end of these presentations there will be a common discussion session where we will be receiving and relaying, addressing, the questions that we will receive from you. While you attend the presentations, you can send your questions through the channel that you have in the YouTube, or if you have problems using the channel, you can also send an email to director@ccam.org. So the email address director@ccam.org, and then we will collect all of them and distribute them, hopefully through an informal and lively dialogue with the 3 speakers. So, as it's today a pleasure to introduce you, our 3 lecturers. We have Eric Linden from the University of Stockholm. He is the coordinator of BioExcel, which is a Center of Excellence for Computational Biomolecular Research. Centers of Excellence are initiatives that are funded by the European Union and which focus on the development of software that is relevant for different communities, for broad communities, to be exploited in the exascale machines that are expected to be deployed in the near future. BioExcel, the Center of Excellence for Computational Biomolecular Research, focuses on the structural and functional studies of the main building blocks of living organisms, covering proteins, DNA, membranes, down also to drug compounds. And BioExcel develops cutting-edge techniques to model molecular phenomena. The software applications that are developed and exploited are among the mostly widely used through the community in these areas. Second speaker will be Jesus Labarta from the Barcelona Supercomputing Center, and he is the coordinator of another Center of Excellence that is called POP. It stands for Performance, Optimization, and Productivity. And this is a Center of Excellence with a different goal, because it provides performance, optimization, and productivity services for academic and industrial codes. So the goal, POP is very transversal because it addresses codes coming from any community interested in trying to improve and to test the codes in this leading HPC environments. So basically, POP focuses on how to exploit these HPC architectures, and does that through a series of services such as parallel application performance assessment, and also the development of proofs of concepts. And finally, last but not least, the third speaker is Paul Kent from Oak Ridge National Lab, and he's the director of CPSFM, that stands for Center for Predictive Simulation of Functional Materials. This is one of the computational material sciences that are science centers that are funded by DOE in the States. And this particular center focuses on the development, application, and validation of parameter-free methods, and also the deployment and offer of open source core codes and scientific data that focus on the exploitation to predict and explain materials for energy applications. So I'm sure today we will hear interesting and engaging presentations from these different areas and approaches to common challenge. And therefore, I mean, without anything else to add, I will give the word to the first speaker, Eric Lindahl. So please, Eric, now it's your turn.
Thank you so much, Ignacio. Let's see, I should share the screen here to get stuck up. Can you see the slide of my presentation there?
Yeah, yes, please.
Awesome. So it's great to join you. This is a bit of a special informal summer seminar series, but I'm going to try to stay with that spirit. So I'm not necessarily going to go, actually, I'm not going to hardly going to go into the centers of excellence at all. But I think it's worth saying that what we do wouldn't be possible without the centers of excellence. And I think it has forced us to be way more professional at what we do. But I'm going to try to share a little bit of, I guess, part of the love story of my life, that on the other hand, we have, as you see behind Ignacio there, we have the protein structures on the other hand, and that's really what we're interested in. But on the other hand, we also have the computers that make it possible. And that has always been a duality with me, and I very much enjoy both of them. And that's partly what this presentation is going to be about, how this has evolved, how it will have to continue to evolve in the future, and both some brick walls that will force all of us to make some hard choices in the future, but also some pretty amazing new opportunities. So what I really do, and what my entire group is focused on, is really understanding signaling in the nervous system. 90% of our applications has to do with understanding, in particular, the ion channels that is set as the receiving end of the small synaptic junctions in your nerve system, and understanding, for instance, tomorrow, if you're having a glass of wine, how is the alcohol actually influencing the signaling and everything. That's a completely different story that I'm going to tell at some other time. What this needs is that it requires models and understanding of relatively large systems, or large, everything is relative, right? But these channels here might be in the ballpark of 30,000 atoms or something, and with a lipid bilayer and everything around it, you might be looking at 100 or 2 or maybe 300,000 atoms. So by traditional molecular scales, they're fairly large. They also move and undergo a ton of different conformations and everything, which is challenging if we really want to convert computer simulations to biology. But I'm going to start by taking a step back, fairly far back. So this is a movie I got from Mike Levitt a few years ago, based on a paper they wrote for Scientific American in 1977 or so. So in 1976, there was a first SECAM. Let's see if we can. Yes, there we get it paid. There was this first SECAM seminar series, where there was a 4-week workshop where the first molecular simulations were done. And 44 years ago, virtually all the systems we could study, people were simply so amazed that you could understand motions in proteins and everything, and that proteins were not completely rigid, hard molecules. We've come a fairly far, let's see, we see the protein here. So we've come a fairly long, oh yes, now we're seeing the front side of the molecule here. So this is BPTI, a classical workhorse that others in Martin Karp's group are also working on. And in hindsight, these molecules we're seeing here, we're seeing them over maybe 10 picoseconds or something. And without water, I would even say that these models would likely fall apart if you were to simulate them for a microsecond. But these simulations were nevertheless remarkably useful, because they forced us to change how we look at proteins. And I think it's easy to forget that simulations actually provided a landmark change in biology and how we consider the actual molecules of molecular biology. And since then, we've had almost 35, maybe 40 years that have been a free ride here. As computers have gotten faster every year, we've been able to reach longer timescales, we've been able to study larger systems, and there's been a wealth of science produced. The problem here, though, is that that's gradually stopping, partly due to the way limitations of computers and everything we can do. And I'm going to come back to that. So classical MD is actually dirt simple compared to some of the other techniques that you've seen in this series. That what we do is that you have some sort of input data, which could be the conformation of a protein, and then I calculate the potential and forces in all these atoms. there are a few equations here, but well, those of you with some experience in the field already know this. If you're a beginner, these equations are also dirt simple, because in contrast to quantum chemistry or anything, here we do it with semi-empiric parameters, pretty much ball and stick, and just try to approximate things to make it fast. And I would argue that on the one hand, it's a horrible piece of dirt, but on the other hand, this was Ari Warshel in particular, amazing invention that we can cheat in MD and parameterize this to reproduce experimental properties. And that's arguably why it has been so successful. MD is very much focusing on reaching relevant timescales and being able to calculate not just the energy of one conformation, but all the billions and trillions of different conformations these proteins go through. And then it's just a matter of moving them a little bit and updating the coordinates. And sorry if that is simple repetition for a few of you. Now, the part here that starts to relate to the duality of the computers is that these are expensive to calculate. We need to calculate them a ton of times. And because computers were so slow, this entire field evolved for decades about trying to optimize floating point operations, or rather optimize away floating point operations. It's pretty sad. Even I'm not among the older people in the field, but the fraction of years that I've spent just optimizing away floating point calculations would make me cry if I think deep about it. If you see the lowest term there, that's the Lennard-Jones interactions. You have a C12 repulsion, R to the power of 12 repulsion term and R to the power of 6 dispersion term. In principle, that shouldn't even be R to the power of 12. It should be an exponential, but on most computers, it's so expensive to calculate an exponential, hundreds of clock cycles. So what we do is that we cheat, and if you already have R to the power of -6, it's just a matter of one multiplication, squaring that term, and then you get R to the power of 12. So even the limitation of computers has been so fundamental here that it's even been parameterized into decades of force field development, whether that's good or bad. And the reason why this is hard is that even for a small system, 100,000 atoms or so, each of these atoms has a ballpark of 500 neighbors. We typically maintain that with some sort of list that you update every 10 to 20 steps. And if you do a bit of math there, that leads to the ballpark of 50 million interactions per step, 2 billion floating point operations per step. And you would all like to complete this in well under a millisecond of real wall clock time. Otherwise, we're not going to be able to get anywhere. And this is starting to be a very hard problem, in particular if you want this to become twice as fast every year or so. Oops. On the other hand, we are getting this free ride with faster computers all the time. So by sticking to small systems, that's the first piece of homework we should do. If we could simulate in the ballpark of 1 microsecond per day, that's roughly where we are today. You can understand an amazing amount of motion, even bordering biology. 10 microseconds per day, we're going to be reaching that in a few years. That means that we can predict emotions, we can improve experiments, and we can understand experiments. 100 microseconds per day, that starts to be challenging. We might be able to replace some biochemistry. And if you actually want to do real medical or biology experiments in the computer here, you probably need to be in the ballpark of milliseconds per day. And that leads to corresponding challenges on the amount of time each step can take. And towards the lower end here, if you want to do a millisecond per day, you would need to complete everything in a few hundred. An entire step would have to complete in a few hundred clock cycles on a modern processor, which is impossible today. On the other hand, we are getting much nicer computers. Sorry that I know it. In the interest of time, I might skip this. So one way to make things faster is to do less. So for instance, having less solvent, that means that there are fewer things we have to compute. If there are fewer things that are compute, things will go faster. You can also compute fewer things by learning to take longer time steps. If each time mistake is longer, that means that we don't have to evaluate all those forces as frequently. And an obvious way to do that is that the fastest motions here has to do with the vibrations of bonds. And if we remove those vibrations of bonds, that means that we, instead of taking 1 femtosecond time step, there might be 2 or even 3 femtoseconds. And that will effectively mean that things are almost 3 times faster. And there are a bunch of algorithms that involve to do this. You can even do fancier things by completely removing some degrees of freedom, such as hydrogens or so. But the whole point, the unifying factor here is that in real life, it's not just a matter of taking one piece of code and making that piece of code go faster. We can actually be smarter by avoiding to calling certain pieces of the code in the first place. Now, this will make the algorithm much more complicated, but it will make the actual simulation go faster. The reason why this is important has to do with the way modern hardware looks. So this is just a single core on a modern processor, even not that modern, the Intel Skylake. One of these cores can do up to 64 floating point operations per cycle. And if you're some more modern cores, such as the Fugaku, the ARM64 machines, that they can do 128 flops per cycle just for a single core. So these, we think of a core as one processor, but it's in many ways it's probably 64 or 128 processors inside that single core. That's just a single core. You can't even buy a single core. My clock here has at least 2 cores. So if you start looking at the actual die, things become even more complicated. So this is roughly the size of my first ever cluster in Groningen, 18 machines. The difference is today you get 18 machines inside the single die on a medium-end processor, even on a desktop. So a modern single processor has started to look very much like a cluster looked when I was younger. And this leads to some pretty big challenges, but even these traditional processors are extremely parallel. The sad part is that they're no longer faster. The clock frequency does not go up. And that comes back to the part that on the one hand, this is a pain in the A, but on the other hand, it's a formidable challenge, right? That how do we make the simulations go faster by exploiting this parallelism and making computers able to do tricks they couldn't do before? So what I'm going to spend the rest of the time doing is really talking about how we parallelize the whole algorithm molecular dynamics, how far we can parallelize this, part of things we've done in BioXL, and also where the future challenges are. So on the one hand, it's hard because it's a sequential algorithm. I can't take steps 2 until I've completed step 1. On the other hand, it's an eminently parallel algorithm because all these forces, they're independent of each other. So the different color windows here in the middle, they can be calculated in parallel on different cores. And calculating parallels was both we and many other people have done. Some 20 years ago, there was a poor graduate student at Stanford working with us who had to start porting our code to GPUs. So this was a GeForce 4 MX, really nice GPU at the time, and really horrible by today's standards. That student eventually got GROMACS running on these cards. It was horribly slow. It was like 10 times slower than a CPU, so we never used that code. On the other hand, this student was Ian Buck, so he continued on to a career at NVIDIA and is now vice president of accelerated computing at NVIDIA. So he's done reasonably well, even though we never used his code. But what both we and others have tried to do is increasingly use these modern processors, in particular graphics processors, and increasingly offload more and more stuff to them. Because what GPUs have an abundance of floating point operations. And remember that the one thing that this entire field was about is that we need floating point operations more than anything else. So what you do both, in particular in GROMACS, some other codes do this slightly different. So we want to use both the CPU and the GPU. And there are a couple of reasons for this, but looking at the past as well as the future, for me, I think it's today we have CPUs and GPUs as different type of processors, where CPUs are really good at random access control flow, while GPUs are floating point monsters. But just as integer and floating point units were different and gradually converged to be part of the same processor, I am actually convinced that within a few years or so, we're increasingly going to see these as different types of functional units in one processor. So what we do is that we have some parts of this code run on the CPU, anything that has to do with parallelization, creating neighbor lists, while the really heavy part, in particular the big part in green here, calculating non-bonded interactions that we try to offload to these type of accelerator devices. We do a ton of fancy stuff here. So for instance, when we run things in parallel, we first do the local work, and while we're waiting for communication, then we do the remote work, and then we send all that off. But in the interest of time, I won't go through that. But what this forced us to do, and what we kept tearing our hair off in the beginning, but that we're kind of enjoying now, is that many of these things that were fundamental truths in our field, developed in the 50s and 60s and 70s, we've had to go back and revisit them. So one of these things has to do with the so-called Verlet list, that we have a list of atoms that were in proximity together with some sort of buffer, and then upgrade that. Had you asked me when I was a student, I would say that these are some of the algorithms that will never change. The problem, though, is that that list looks different for every atom. And that's something that GPUs in particular hate, because you have a ton of functional units, but they need to execute exactly the same type of code. Otherwise, you're never going to be able to utilize the floating point operations. So we had to express this as a way that instead of having the traditional gridding and then a list for all particles of equal length, we effectively create regions where quartets of particles, effectively small tetrahedra, interact with other quartets of particles, so that you always have 4x4 interactions as so small tiles. So either all particles interact between those or none of them interact. And this is something that GPUs in particular love, because we can calculate 16 interactions when we load 4 atoms. We have developed this in a very generic fashion so that this works for pretty much any CPU architecture you can imagine, but also any GPU architecture you can imagine. And this is an important concept that we're seeing both in molecular dynamics, but I would argue in all these computational science fields, that historically we've tried very hard to avoid floating point calculations, and that's completely changing now. Because the goal is not to avoid floating point calculations. The goal is to make the program go faster. And these modern processors are so fast that it's frequently better to accept the penalty of calculating more floating point calculations if that means that we can handle memory more efficiently. So what you see here on your right is that as we're moving to larger and larger clusters here, the efficiency, the relative efficiency of the algorithm actually goes down, but the absolute performance will go up because we are able to keep the GPUs in particular, but also CPUs 100% busy. What that effectively means is that it's hard to tile a circle. It's even mathematically impossible. So instead of having a beautiful circle, we end up having these, it's not quite a circle, but it's a bit expanded of a circle. So this green tetrahedron in the middle, it's not really a tetrahedron, it's just 4 random atoms. They will interact with all the black atoms here, which effectively means that we end up wasting some of the resources and calculating extra interactions. It's not too horrible on a CPU. The only problem is that this 4x4 setup is not efficient on GPUs. We need to go to even larger, so 8x8 or 16x16. So on GPUs, we expand this, and then we have these 16 atoms in the middle. That's effectively a supercluster. And that means that there would be theoretically, there would be a ton of zero interactions here, so that the first algorithms we wrote here actually meant that we wasted 75% of the floating point operations, which would make me cry in shame if I had asked my 30-year younger self. But it's still faster in GPUs because they're so remarkably fast if you just feed them data. Now, what we can do, though, is that it turns out that we can optimize away quite a few of these things. I'll get back to that later. But for now, you can think of this having a very inefficient neighbor list that has tons of zero interactions included, but they're still more efficient on modern processors. What this enables us to do, though, is that all this complicated stuff we tend to calculate on the CPU. And the advantage with this, we can do this in parallel. We can do all the fancy optimizations and everything. It doesn't really matter because the CPU is really good at this. And once this is done, we send it over to the GPU and the GPU just consumes it. There is a list pruning part. Let's see. No, it wasn't circled. There was this list pruning part there in the middle. And that means that we can actually optimize away a few of these things on the GPU later, but I'll come back to that. What this enables us to do is that it enables us to calculate some of these non-modern interactions remarkably fast. Remember how I said that we needed to complete this in well under a millisecond? So this is a bit of a strange plot, but it compares how efficient we are. If we look here at the system, let's pick a tiny system of 10,000 atoms. That would be roughly the 12 bar on the x-axis. But 12,000 atoms, the throughput we get is in the ballpark of 200 atoms per microseconds. So if I do my math there, that something means that the entire non-bonded interaction kernel in that case would complete in the ballpark of 60 microseconds, which is insane. That's not the full MD step, but the actual non-bonded interactions would get complete in well under 100 microseconds. And that would mean that we're not at a milliseconds per day, but we're well over 10 microseconds per day. Now, then we have to factor in parallelization and everything, so it still gets hard, and 12,000 atoms, it's a tiny system, but it just goes to tell how incredibly fast these accelerator devices are. But the other thing that we can do, remember that I told you that we end up wasting a horrible amount of interactions. The reason for all these neighbor lists is that traditionally we needed to avoid calculating zero interactions, but if we accept calculating zero interactions instead, it turns out that there are lots of cool tricks we can do. So instead of having a neighbor list that we update every 10 or 20 steps, maybe we should go to a neighbor list that we only update every 100 steps. That would need to have a gigantic buffer so that we don't miss anything. And normally that would be horribly inefficient. It turns out that it's not that inefficient on a GPU actually, because calculating those interactions is so fast. But the other thing they can do, that once we have a finished neighbor list, it's reasonably easy to just go through that list and check, tile 47, is there really anything to calculate in tile 47? If there isn't, well, we can check that every 10 time steps, and that's reasonably easy to do even on the GPU. And remember how fast the GPU was at going through things. So we can now have a second inner loop where we start with our large neighbor lists, and every 10 steps or so, we prune this down to a significantly smaller neighbor list. And this turns out it's going to work miracles on the GPU. So we do that here. The first thing, when we get things to the GPU, we can start pruning the list. Now that's a bit bad, because that would mean putting this in a critical path that we can't calculate the non-bonded interactions until we've cut down this neighbor list. But we can even do this after the fact. So while the CPU is busy doing integration, normally our GPU would be idle, which is bad. But while this GPU is idle, he can start pruning, checking the neighbor list. You know what? Can I prune down this neighbor list a bit more? It doesn't really matter whether we complete or not. If we don't complete, we might end up calculating a few extra interactions, and then we just start repruning next step and next step and next step. And this is a pretty neat way for us, at least, to keep both the CPU and the GPU close to 100% busy and getting really good performance. The other embarrassing thing that happens, I used to tell my students that, when it comes to optimizing code, that's the one thing I know. If you can improve my code by 1%, I would either eat my left shoe or buy you a new laptop or something. The only problem is that Szilard Pal has been a bit too good at this. I don't make promises like that anymore. So what suddenly happens is that when we take this stupid, horrible code that now uses way too many floating point operations, and then you port it back to the CPU, it's 20% faster. And the reason for that is, of course, a modern CPU looks much more like a GPU than it does like an old CPU. And that's a memento mori, I think, for all of those of us who are professors, that a modern computer does not look the way a computer looked 20 years ago. The third thing we can do is that when we have both CPUs and GPUs, we can balance quite a lot of things. Part of the electrostatics we calculate with particle mesh eval. And with particle mesh eval, we can choose, depending on how long I make my cutoff and how coarse I make my grid, I can choose to calculate some things in reciprocal space and some things in direct space. But the relative volume of these things I can adjust. The relative tolerance, the tolerance and accuracy of the electrostatics is going to be the same. And for GROMACS, at least, this is something we do on the fly at the start of each step. So we find this minimum, and in this case, it's going to be roughly 1.25 nanometer cutoff that gives us the best performance. It's a wall time of 3 milliseconds in this case. And this goes on. I'm not going to go into detail about all the things we've uploaded, but as these accelerators have gotten faster and faster, we first started by enabling you to offload the particle mesh eval algorithm to the GPU too. And in the version of GROMACS we released a few months ago, Artem Shmurov has generated a beautiful, almost complete offload implementation where even the 3D FFTs and the integration can be offloaded to the accelerator. But we can still do the parallelization on the CPU if we want to, and anything special like fitting things to a cryo-EM density or so we can do in the CPU. So with this, I'm not going to go in. The point here, the relative performance of GROMACS here is not important. I would argue that most programs have gone through iterations like this. But what I want to draw your attention to here is that what used to be a free ride when that processors get faster all the time, that doesn't happen anymore. But all these programs, not only GROMACS, have gotten like a factor 3 to 5 faster the last few years. based on new algorithms that are able to use increasingly parallel hardware. I would actually say the clock frequency of the last cluster we bought is lower than the clock frequency of the cluster we bought 5 years ago. On the other hand, we probably have a factor of 10 more functional units. But the reason we can use those functional units is that both we and several other groups have developed algorithms that are able to scale, parallelize better, and also use more types of heterogeneous parallelism in these problems. So on the one hand, we can use CPUs that I have on the left. You can even saturate a CPU with just a single core. So I can put 8 GPUs in a node if I want to. And some of these very fancy and expensive new machines, such as from NVIDIA, where you have, say, 8 or 16 GPUs in a super expensive box where all the GPUs are connected directly, we actually scale reasonably well. This is a system with 1 million atoms, but we can scale over 16 GPUs in a system. And my hunch is that we're all going to see much more of these so-called fat nodes in the future. So, think of one node with 32 accelerators that are a factor 5 faster than today, connected super tightly to each other. It doesn't always work. We're not there with particle mesh eval yet, but we're working on it. But if you're starting out in this industry, that's the type of system I think you should focus on, getting your code to scale over 32 GPUs for a tiny input. And gradually, I think that we've been able to find a ways where we have tons of parallelism. So this is, we've divided the system. So part of the system is handled in real space, part of it is handled in reciprocal space. We have roughly 3/4 of our resources to the real space, to the remaining reciprocal space, and then we do very fine-grained domain decomposition and load balancing and all of this. And this is probably not the load balancing a computer may. Good computer scientists like Jesus would do this, but this is horrible because that we don't have the same computational load everywhere. It's more expensive to calculate a protein than in water because waters don't have torsions, for instance. We do all types of fancy optimizations depending on how things move. So every cell here has a different size. And while we're less concerned about the relative scaling and scaling to 1 million nodes, we are super concerned, on the other hand, with the absolute performance. The price we pay for that is now that a small system here with, say, 1 million nodes will never scale to an exascale resource in itself. So on the one hand, you could argue that's game over. And that would be bad, in particular because we're funded to get things to scale on these large systems. And somewhere here, we're going to need to find different approaches. This is not, part of this is shortcomings with codes, but part of this is a much more fundamental shortcoming. Remember the first plot I showed you that the entire field here has optimized the wave floating point interactions. And I think if you do the math for a small system, if you have 2 billion floating point operations, there simply are not enough floating point operations to scale that to the largest resources in the world. And I'll show you why. So this is an old plot I made, very old. I've never removed anything from this, but it's over 10 years old now. So once upon a time, when I first made this book, both Jaguar and Europa, I think it was called, or Eugene, they were amazing new machines in Europe. In 2010, no, there was Eugene, 300,000 cores or functional elements at the time, amazing. If you just apply Moore's law here and imagine as we're getting more transistors, if you convert that into functional elements, how would they develop? Around 2012, you used to have 1 million cores or functional elements, and there was a machine called Sequoia by IBM, so we roughly kept track with that. 2014, 3 million cores. 2016, 10 million cores. Did we get that? We actually did. Pitt Steins in Switzerland. Well, not really cores, they were GPUs, so that I'm going to keep calling them cores, but it's probably fairer to call them processor elements because they're not really independent. In 2018, we would have had 30 million cores, and that happened. We had Summit. Again, not really cores, but processing elements, and there were 125 million of them. So the point is we're even well ahead of this curve. 2020, this year, we should have had 100 million cores. And if those of you who have kept track with the top 500 list might have seen a machine called Fugaku. Fugaku only has a bit over 7 million CPUs, but those CPUs are marvels of parallelization. Remember my initial slides. Don't think of that as a core. Each of those CPU is really a cluster internally, and they have at least 32 different processing elements that can do a fused multiply add operation. If you do that math, it effectively has a bit over 200 million processor elements. So now we're more than a factor 2 ahead of this curve. By 2022, we would have 300 billion cores, and 2024, we're talking about 1 billion processing elements. So those of you who are students here now, well before you're going to get tenure or anything, the question you're going to need to ask yourself is, how are you going to use 1 billion cores? And this goes back to the statement I just made. There are only 2 billion floating point operations in that first simulation I described. And there is no way you're going to be able to parallelize things so efficiently so that each functional element only does 2 floating point operations, because that's one FMA operation. It's not going to work. You're not going to be able to synchronize things every clock cycle. And as horrible as that is, I think that's amazing, because once you've hit the brick wall, it's time to give up, and you need to think of a completely different way of doing this. And I think what both we and others are heading to is that we're going to need to find different ways of doing things. When this 1 billion processing element machines comes into play, I suspect that somebody's going to come up with an idea of using this to simulate a gigantic system, such as on an entire cell or a few cells. Here's the input of that simulation. We have developed some amazing time machine technology in my group. So if you look carefully now, I'm actually going to predict this is the starting confirmation. At the start of that after those 6 months of simulations, this is what the end confirmation is going to look like. Because if you try to simulate an entire cell, you will likely only be able to simulate it for a picosecond or something, and there's absolutely nothing that's going to happen with an entire cell in a picosecond. Don't do that. Instead, what I think the entire community is moving towards is really ensembles of different algorithms. And I wish I had another hour, because then I could go into deep details about this. But I'm just going to spend 2 more slides just whetting your appetite a little bit. That as the individual simulations are getting more and more efficient, what we can do is that we can combine those individual simulations, maybe using a few hundred GPUs or so, but run tens of thousands of them. Now, historically, that would just be brute force sampling. And brute force sampling certainly works in some cases. But you can also combine that with various types of statistical models. Anytime you have a type of processor or something, if you just throw out thousands of simulations, even if you just do brute force sampling, we can analyze those after the fact and cluster them. For instance, to kinetically to see which of these states appear to rapidly and to convert to each other. That would be a Markov state model. And based on those, you can identify larger clusters, macro states, for instance. And this could be an ion channel, for instance. It could be an open and a closed and a desensitized state. And once you have these states, you can start analyzing in terms of, so how likely is it to move from open to closed, or from closed to desensitized, etc., and build up a more macroscopic model. And there have been a number of groups that have been successful with this. It's also one of the things where I think folding at home has made a tremendous difference, mainly because folding at home helped us answer some of these initial questions. That is the challenge for molecular simulations, that our force fields are not accurate enough, or that we were orders of magnitudes behind on sampling. And in that case, it actually was sampling. We were horribly bad at sampling, that it wasn't a matter of reaching 10 milliseconds or 1 microsecond. We reached hundreds of microseconds or milliseconds, or even hundreds of milliseconds. And that has been like turning a page. We understand a whole lot of these processes. We're certainly not perfect, but we can understand the sampling. So to sum up, just one example, that those initial ion channels that I mentioned, that we are actually approaching them increasingly with Markov states models. So this is something, unpublished work that Catherine Berg in my group has been working on right now. So this is a small channel that can open and close and desensitize. But what Catherine has been able to do is explore these channels under different pH. And rather than seeing one opening and one closing event, she can then use simulations, hundreds of simulations, each reaching several microseconds, to map out the entire space in some sort of low dimensional landscape. So at low pH, at low pH, the channel would be either open or closed. You would have a small open population, although the large one would be closed. But if you move to high pH, the open population completely disappears and the channel would only be closed. And this actually corresponds remarkably well to what we're seeing in experiments. But what the Markov states model increasingly enables you to do, rather than just getting the landscape, you can also separate these into clusters of different open states, different closed states, maybe the desensitized states and intermediate states, and identify each intermediate cluster and calculate transition rates so that we actually see how fast do they interconvert to each other. And this is just one example, but rather than just getting snapshots, you can actually then start to see that how do the channels open, not just with one snapshot, but which way is the most likely way for the channel to open. And this is to me, it's a completely different way of studying the physics. It is statistical mechanics, but suddenly we're applying statistics, not just to sampling confirmations, but to our entire understanding of the concepts. And there are a number of frameworks, not just using Markov states models, but really using simulations on a higher level. And if you're getting into the field now, I think that this is where we have some of the greatest remaining challenges. In the interest of time, I'm going to stop there. The GROMACS project would not have been possible without a number of people, but in particular, Bert Kess and Szilard Tal, that we should thank you. Paul is our project manager, and Artem has been tremendous in achieving this, our GPU-only port. And then we've had tons of help from several vendors, and I should also give CSCS and in particular BioXcel credit. And you, thank you for listening.
Okay. Eric, thank you very much for this very clear and engaging presentation. And as I was announcing at the beginning, now we will move to the second speaker of today. I remind you that you can always pose your questions through the YouTube channel or email them to director@ccan.org. So, Jesus, now please, it's your turn. You need to unmute yourself, Jesus.
Unmute myself.
Exactly.
I'm okay now?
Yes.
Can you see my screen and my mouse?
Yeah.
Perfect. So I'll be trying to talk about the POP project, but not only about the POP project. In a sense, I will be giving and presenting a lot of personal perceptions and personal statements about what is the objective or what are the techniques and challenges in the area of covered by the POP project itself. I will mention a little bit about it to start with, and then I will go into some of the components, which is mostly the performance analysis and how I feel things are happening there or evolving there. And about programming model and practices. It will be much shorter on the programming model stuff. I will be focusing mostly on the performance analysis area. And the POP project is another center of excellence, which with the idea of providing an external view of what's happening with the application. Sometimes developers are very focused on their day-to-day activity and their existing and current approach, and it's potentially interesting to get an additional external view by what we consider, the way I consider me myself mostly is kind of an analyst, okay, performance analyst. And I can make suggestions about code refactoring. So this is the kind of things that we try to do. And for this code refactoring, try to promote best practices, ways we think are the best ways to achieve good efficiency or to achieve productive programming. So that's the objective of the project, with partners who have been active in performance tool developments, in programming model development. So the idea is to try to expose some of the experiences and some of the techniques that were used. But the first point is just to state where we live. So you have been seeing, and Eric has been giving good examples, and in the seminars, in the webinar series, there's a lot of examples of computational science type of studies and simulations. We live on the right-hand side of this plot, more on the pure computer science, not specific to one area of the application, not specific to certain techniques or numerical algorithms. It's more on the basics of essentially how to program, how to use the computers in a sense, would like to provide ways and tools or mechanisms to have even between these communities. Sometimes I feel there's a little bit of disconnect between some of these communities, and we try to put a transversal approach which can do analysis which are kind of valid or for all of them. I will be focusing, as I said, on two technologies because I think they're very, very important. One of them is programming models and how to decouple the programmer from the machine, the program from the machine, how to make doing that in a productive way. And the other is performance analysis tools. The point is that technologies is nice, is fun, it's what we like to do, but they are not necessarily the most important thing in life. The most important thing, I think, is how the technologies are used and how people uses those things for getting better results, better understanding of the systems. So I will be talking about these two topics. First one is, and I will start by talking about performance analysis tools and giving you some of my views and some of the things which I'm kind of sometimes certain feelings I have. And probably this is the first one about performance analysis. So you need to use tools. And really there is a little bit of a difference from my point of view on what are the practical tools in science and the practical tools in computer science, and a little bit about the way we use them, okay? The tools, I think they are very, very important. The ability to measure determines your ability to derive insight and advances in science. And I think it happens quite a lot, quite a bit, that in computer science we have printfs and we have timers, and this is what we essentially use. We, of course, try to develop use tools that go and are able to squeeze into the internals, into a lot of the detail of the behavior. But in reality, practice, I have a certain feeling that all the performance analysis on the performance done within the performance analysis groups, let's say, or even within the domain groups, a lot of these things are very speculative. It's very much based on, we see a number and we talk about the internal microscopic behavior and the evolution of the function of time, how that number was generated, what it is due to, and how to refactor the codes. I think this happens a little bit. And I want to say, or I would like to say that in reality, the instrumentation and measurement of the behavior of the system itself, this is really a really good problem for kind of the type of big data or analytics or applications that we are seeing in many other domains. I mean, it's trying to gather data. By the way, I mean, if you talk about, as Eric mentioned before, if you talk about 100,000, 100 million cores generating information about their behavior every few microseconds, that's really a big source of big data. And the question is, how do we analyze and understand that behavior, the internals? And the very frequent, I think the practice in performance analysis is there's a lot of data, or there could be a lot of data, but we very early, very rapidly aggregate it. We generate essentially just profiles, very often linked to a syntactic perspective rather than to a behavioral type of perspective. And I think this is a kind of situation which I would like to stress the importance of really doing further in-depth analysis, looking a little bit more about the variability. So not only aggregated numbers, but very, I mean, simple, stupid things like about analyzing histograms, analyzing correlations, these kind of things, these kind of practices could give a lot of information on the performance of applications, about the space-time behavior of the programs. Is what is the structure? Is the pattern really repetitive or not? Or what are the differentiating aspects that determine that space-time behavior? And this is one of the kind of things and approaches we're trying to push in the POP project, a little bit looking at the details of the internals. At least ourselves, we try to go into those details because you end up learning about a lot about the behavior. But in reality, there's a lot of potential for analytics for each. Let's say if you take every computation bars between exit of an MPI call to entry to the next one, you can build your feature vector where is features like instructions, H.P.C, or cache misses, or branch mispredicts. And you can build a feature vector with tens or hundreds of metrics. And how do you squeeze it or navigate it or process it to really obtain insight on the behavior of those computational regions? And we have been using in the past a lot of clustering techniques. We have even using things like using sequence alignment algorithms, considering that in reality threads are kind of different sequences, which in reality should be very similar across processors. So you could understand and analyze what are the relationships between different processes. We've applied a lot of techniques to finding out by combining sampling and instrumentation techniques to get microscopic evolution of metrics like instantaneous cache misses, but also instantaneous MIPS or instantaneous evolution of metrics a long time while sampling at relatively low frequency and combined with instrumentation. Not only for the metrics about the performance of the core, but also things like memory access patterns. What is the regions what the regions of the address space which are loaded, read, stored, written during the execution of the different regions of the program. We have used tracking techniques to see how these regions of a program evolve when you, for example, scale. Do all of them keep their H.P.C? Do they improve their H.P.C? What is the fundamental reason for that? So there is a lot of these analytics that I think is, and in our case, what I wanted to share is kind of a little bit of feeling that these kind of techniques, we have been developing them for a long time. It's in real practice, even on the POP assessments, they are just at the very end. So most of the analysis even go to the simplest, use the simplest features of these capabilities, which would allow us to detect the structure of the application, but also to this scaling type of behaviors analysis. We try to use them, and we try to use them to give insight on processing the data, the snapshot of what we have obtained on a given trace. But there is a lot of room. I think there's a lot of room to leverage more additional techniques from the people doing analytics in general in many other fields, in the same way that we use things from sequence alignment or from even signal processing. There's a whole bunch of possibilities of applying new techniques and getting new techniques here. If I go to another aspect of the analysis, is not only a matter of measuring and how you present the data that you have measured, it's about how you build models. And these things may not be the reality or the full reality. You are not counting quantum effects or whatever it is, but it's amazing the dynamic range, how these things have been used and how long these things have been used to really do a lot of engineering. So I have a certain feeling that if you look at laws or models in computer science, even if you take under law and you see how it fits reality for many codes overall globally, it's probably not that great. I mean, there is still, we are a little bit in this situation where we use computers to understand molecules, as Eric was saying, or materials, but it's the saying in Spanish is the blacksmith eats with a wooden spoon. I think in English the equivalent thing is the shoemaker's son going barefoot. So we use the computers to understand all many other areas of science, and we don't use them that much to really understand and model our internal behavior. And when you, the other thing is probably sometimes people, I have certain feeling that people tries to blame very often models, saying, no, the model is wrong, it does not much. I would like to highlight this statement by George Box. I mean, don't worry, all models are wrong. The only thing is, are some of them useful? Can you get useful models that give you a good description of natural phenomena? A description that you can use to understand the behavior, and you can use to act and counteract the measures, the fundamental causes that generate those difficulties. And I think one thing that happens in performance analysis, when you have, if you try to say, oh, I have this very powerful, very analytics and very capability of computing many metrics and for very specific. If you start going into that very low level detail, it's kind of a very fuzzy, it's a huge search space, it's very fuzzy, not well defined. And finding the real fundamental problems and how to abstract and present and summarize, make a model of the behavior of the system is really difficult. You end up is this thing of the trees that don't let you see the forest. Okay, so the question is, can we do models? So I'll be talking about this model. Can we do models that let us describe in a very succinct, very small few parameters and describe fundamental aspects of the behavior of parallel programs? And this is a kind of model that we have been pushing for and evolving and using on real applications with POP, where you describe the efficiency of your program with just 3 numbers here that characterize your parallel behavior and 3 numbers that characterize a little bit your computational behavior. So, and these are fundamental models, fundamental factors that they have to do with parallel computing in general and not with a specific detail, a specific machine, a specific application. Their fundamental is how much of your performance is limited by load balance, how much of performance is limited by transfer itself, by the fact that speed of light or speed of communication is not instantaneous, and how much is limited by serialization effects, which actually means somebody I wait from you, sometimes you wait for me. Overall, we might be well load balanced in terms of total amount of computation that we do, but we might have these idle times because of not perfectly balanced distribution. So these are 3 numbers that characterize one application. On the parallel side, there are 3 numbers that characterize the performance of the application. We have seen, for example, Eric saying the trade-off now, it might be worthwhile to do more computations, more instructions, because that might help you improve on the other side. So, but it's good to quantify and to know how much of this code replication are you doing or not. It's important in current systems to quantify what's the frequency of the device, and good old times where we knew the frequency of the cores have gone. This is going to be totally dynamically changing, and really it's good to know this might cause, may not, but may cause some issues. And then there's another factor, which is the scaling of H.P.C. How does H.P.C evolve when you scale? So these numbers, of course, you can compute them with a certain kind of models from the raw data that we capture, but essentially you get some numbers that tell you overall a very general perception of how good or how bad are the fundamental aspects of the behavior of your application. And it's a very high level model, high level description, and which is transversal, orthogonal, can also serve for any different kind of application domains, and actually may help people in different application domains which expose similar type of fundamental difficulties could even actually discuss. In our case, we do a lot of studies based on just trying to obtain these metrics, and from here on, of course, you want to further investigate, you want to further know what is the reason why this efficiency, this aspect of efficiency is not ideal. I will, before going a little bit more into this finding out the reasons for the idealness or not of the model, I want to talk a little bit also about machine models. I mean, and they are not that much used in the performance analysis area, and I think this is really a methodological thing that is missing in our approaches to performance analysis. People use, maybe architects use machine models at very fine grain and Gen 5 instruction level simulators or these kind of things. the granularity at which you use those simulations might not be amenable to do real analysis of large codes. But the question is, I think, a little bit more than what most of us do, most people does in terms of modeling would be really good. I mean, we are, in this case, we are using a model of the MPI type of activity in a node, and what are the fundamental components of that might restrict performance. Is it contention? Is it actually bandwidth? Is it actually transfer latency? Which are these the impact of the really fundamental abstract set of parameters without having to model really an extremely detailed specific architecture. So I think these models, and using more of these models, is something that's actually missing a little bit in the dominant practice in the performance analysis, and it's something that we try to push, and models that can let us understand what if we were to have a faster or a slower network, what would be the difference between different encoding approaches. Very often, our experience is sometimes people claim, oh, non-blocking calls is the way to overlap communication and computation. And maybe yes, but maybe not. Maybe, and you gain performance by refactoring a code from a blocking MPI calls to non-blocking MPI calls. But a lot of people does this transformation. That's many other things that go beyond the actual explicit use of one set of calls or the others. So comparing the impact of different architectural parameters on the code's performance is something that can give us a lot of additional insight. Also, by the way, we use these simulators in terms of the way, if I go back to the way we construct the few simplified models. One of the important metrics, one of the important ways of doing it is we do what if analysis of what happens with an ideal machine, infinite bandwidth, zero latency. So the ideal thing, I don't know how much would you pay for that, okay? Or how much would people pay for that? Very often it's not worthwhile, but at least conceptually, it is a nice way to give us structural insight about the characteristics, about the dependencies in the program. So we have these many different parameters that can influence program behavior. We have these abstract models of describing a given program behavior at a high level, and there is a lot of possible interactions and causes between those of them. So it is good to have a first level model, which is an abstract model. But in reality, if you want to dig down, and we should dig down, because actually the recommendations is not as easy as saying transfer efficiency, you should reduce number of messages or reduce message sizes. Well, there's maybe yes, maybe not. Sometimes and to what extent these things happen or not, or to what extent this happens in one part of the code but not in the other. So the point is, you need to really do composition of the models and the analytics and a lot of navigation in this fuzzy space. And you can really find out the details of why there is computational imbalance. Is the computational imbalance because of real instruction imbalance between processes? Is it because of H.P.C differences between processes? Is it because of I don't know, operating system preemptions? Or so one should be able to really look down into the details, and that's where one has to go back. So methodologically, I would start by this abstract high-level model, but then digging down with applying all the analytics and all the display and the navigation techniques in order to try and understand what is going on and what happens and what are the probably more productive and less effort, more benefit refactorings and transformations that you may have in your code. And not only measuring the impact of the application itself, because sometimes there is impact of operating system noise, impact of many other characteristics that you could influence your behavior, your survey behavior, and sometimes the conclusion is not necessarily blame this MPI provider or blame. Sometimes the conclusion maybe you should map processes in a different way, or no, sometimes you should refactor the code in a given way. So this is This is the kind of approach and the kind of a typical structure of the studies that we do, where we first look at application structure, and this is one of the things which is very important in itself. And we believe there is not people, sometimes is not totally aware about the actual behavioral structure of the codes. And this is an important component. Then we do these efficiency models and look at the individual factors. Why is actually, what is causing performance imbalances? And once you have pinpoint these things with detail, get driven by the global efficiency model, then you can come out with specific recommendations which we believe are or would be of major productivity. So we have done statistics. We do statistics about which codes are limited by which of these factors, by memory bandwidth, by transfer, by serialization, by load balance. We end up with this analysis. We have covered a large number of analyses. And this is a useful insight for ourselves, for co-design, okay? Even for co-design in part of our other activities. I mean, how do you design the programming model stuff, and co-design is not only a matter of doing architectures, it's a matter of how do I adapt my applications, how do I adapt my runtime, how do I, which is the best level at which I should be introducing changes or supporting functionalities. So very briefly now going to the programming model and practices. Once we have done this analysis of the behavior and suggested refactoring approaches, we try to do some of those. We try to promote some of those. It's probably a little bit, in my case, these are from my point of view, personal point of view, these are some things which are fundamental principle approaches, directions that I think are good in terms of hierarchy and how you hybridize. There are things on how you interact between MPI and OpenMP and what is the impact, how this should be, the code should be refactored. So we are trying to push for more use of nesting. And I know people have some bad experiences with nesting. We're trying to provide best practices on how to get those experiences being positive. There is one other thing which I believe is very, very important, is malleability, the ability of the code to be dynamically adaptable to the environmental conditions. So we propose things, ways of doing it in terms of most typically in terms of MPI plus OpenMP, hybrid codes, and or visions about how to, let's say, homogenize heterogeneity, for example. I think this is something which is really important to have, try to minimize the divergence between many different implementations for many different architectures or systems. And it's something that we try to push in terms of in programming for, let's say, more for the fine grain, for the traditional real parallel kind of thing, which in one program, which would be MPI plus OpenMP, or MPI plus OpenMP plus accelerators. But we believe that this is the same fundamental things happening in workflows. Okay, very much the same thing. So we try to push a little bit of the ideas also there. And one of the important things I believe is, as I said, is this decoupling of the application interface from what the machine has underneath. And here I mean, probably this is a personal obsession sometimes, maybe is try to forget the specificities very much about the specificities of the resources. And I know, for example, Eric, you have been, because you are targeting very, 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 very fine granularities, and sure, for currently you have to do it, but we try to push or trying to find out what would be approaches to get some of that without many of the specificities of a given machine. So I think this is an interesting challenge. It's a real how to offer this interface, that kind of an osmotic membrane that couples the applications from the system itself and conveys through this osmotic membrane as little information as possible. You needing to specify as few things as possible, but able for those two layers to really cooperate and communicate and share, work together towards the final objective of having full better performance, better efficiency, of course, certainly of utilization of the systems. So it is a long road. We are trying to do examples with some of, so after doing some analysis to some of the people, we tell them, would you like us to work with you a little bit on seeing how these visions and these ideas can be proposed, and we are trying to push some of these things of how to use tasks, how to use dependencies, how to use dynamic load balancing libraries that we've been developed, or the task-aware MPI interfaces that really, with little syntactic modification in your source code, let you achieve a significant fraction of all these potential benefits of these techniques. So just to finalize, well, when you get to a certain age, you are like, I don't know, when the old guys, when you go into, you always keep telling your stories of when you went to the army, or your stories from when you were young, okay? So this is kind of some fundamental concepts that we try to push, I try to push, and that I think some of these things on the left are far more important than than many of these other things on the right. And we try to push those as part of, by showing people, looking at their actual codes, their actual performances, telling people what we see in what we look at, and suggesting ways of doing it in a different way. I think it's a difficult battle, because very often some of these things, obsession for some of these things, is hardwired in the genes of a lot of programmers and analysts. But in reality, it's all about that. It doesn't matter how nice or how interesting or how advanced your analysis technique is. What is important is whether we are able to adapt, I think, the mindsets of ourselves as analysts and programmers to what we consider is the right or the better approaches for addressing future exascale. But it's not only it's not for future exascale, it's for today, for currently efficiency of today's systems. So not only for that. So just to finalize, if somebody is interested in getting some evaluation, some assessment, some comments of the performance of their application, we have this, in this web page, we have a link to an application form where people can apply, and the project offers these services of analyzing the applications and giving comments and discussing it, live interaction discussion with the customer, without actually us being a specialist on the final domain, just what we see an orthogonal and external view, which might be useful, or you might decide to follow, or you may not. With this, I'm finished my presentation.
Okay, Jesus, thank you very much for this presentation of the broad set of activities that POP is carrying out. For those who have joined later, I remind you that you can post your questions to any of the lecturers, and in particular to the last one, Jesus, through this channel that you have in the YouTube page, or by email to director@ccam.org. Now we move to the third speaker of today's session. This is Paul Kent from Oak Ridge National Lab. So please, Paul, now it's your turn.
Thank you very much. Can you confirm that you can see my slides and hear me okay?
Yeah, indeed, we can.
Excellent. So first, I'd like to start by thanking CCAM for organizing this very timely seminar series. I've been enjoying it so far. So what I want to do today is really touch on two issues. And of course, I'm going to have to do this at quite a quick broad brush level. I want to talk first about exciting opportunities for new high accuracy materials predictions. And then in the second part of my talk, at a much less technical level, more general level, I want to talk a little bit about some of the challenges we're facing with some of the new architectures. And I think this is going to match up very nicely with the last two talks that we've heard. And for those who are not so interested in materials, I do hope to make a couple of pointers in this second part that I hope can make developing your codes and evolving them much more easy in future. So I'd be happy if I can change some people's actions with those comments. So I'd like to start by acknowledging all the members of the Center for Predictive Simulation of Functional Materials that I direct. As was pointed out in the introduction, this is one of the Department of Energy's Computational Materials Sciences Centers. And in this seminar series, we're actually hearing from a number of the directors, including, for example, Professor Ghali last week. This is actually us at our last all-hands meeting last August. And you'll see that we've actually got people essentially nearly coast to coast from across the United States. So UC Berkeley, 4 national labs, Livermore, Sandia, Argonne, Oak Ridge, and then NC State universities and Brown. And we, of course, have important science goals. We've been mostly focused on the physics of transition metal oxides these last few years, where the techniques that I'm going to be describing are really needed. But as a software center, we have an important mission to develop the quantum Monte Carlo methods and the open source QMCPAC code. So to improve these methods and codes so that we can get more understanding out of the science that we do and the calculations that we do, and also, of course, have a wider user base. And of course, while we're developing this code, I also want to point out we do a whole range of other calculations in electronic structure, such as density functional theory and excited state calculations, for example. And although we don't develop those codes, we are, of course, dependent upon them. And we're cheering for the developers of those codes to also be successful, because they all need to move forward as a big ecosystem. I'd also point out that actually in these centers, we have some experimental validation, both to make sure the calculations are giving the answers what we basically should give, and also to help keep ourselves focused. So why might we need more accurate and predictive methods? I'm showing here 3 sort of general areas where we'd like to really bring predictive theory to bear. I think these are pretty representative. There are others, there's some more extreme cases, but I'll talk through these ones. So first of all, here on the left, there's a lot of classes of material where we need quite a bit of empiricism to model them accurately. And this means it's hard to get ahead of experiment, which is what, of course, we really want to do. We want to be able to predict materials and guide our experimental colleagues so we can be faster and more efficient. And so this is one example. This is a metal oxide, a famous one. And this is resistivity, and you see it has some metal insulator transitions depending on here the substrate you grow it upon. And this is actually representative of many metal oxides that have tunable metal insulator transitions. And this is important because we could potentially make a device or a sensor or perhaps a new form of memory storage or low energy computing out of these. And so clearly here we need both the fundamental understanding, but also the materials relevance, and this is a challenge. The second example I think is a common one, trying to guide synthesis. So in one of my other projects, I work on the so-called MaXenes, and these are now the largest family of 2D materials. And that comes about because they're sort of a sandwich of metal atoms, and you can have many different metal atoms, and usually carbon or nitrogen, or also a solid solution there. And then on top of that, you can have different atoms on the surface as terminal groups. So there's a lot of combinations. And these materials are promising for lots of applications. And for example, they show very, very good performance for capacitive energy storage, some record-setting properties. And of course, we would like to be able to focus our experimental and theoretical efforts on the ones which could give even higher performance. And then finally, in this third area, of course, as theorists, it's most exciting to be able to predict new phenomena. So there's a lot of work on so-called quantum materials, exhibiting new quantum phenomena. And of course, besides experimental measurements, there's predictions that are typically done from simplified models, and these need to contain some parameters. And of course, to get ahead of experiment, the question is, well, where can these parameters come from? How can we be sure the model is appropriate? So these are areas where we would like to have more accurate, more predictive methods, less empiricism needed. So at the same time as we have these science demands, the computational landscape here continues to evolve. And this is the sort of US Department of Energy centric view of some of the machines that are coming along in the next few years. So coming up later this year, there's the Perlmutter machine at NERSC. And this has got the NVIDIA Ampere GPUs on it and AMD CPUs. It won't be the largest machine, but it's going to be a lot more powerful than the existing machine. And this machine is, I should stress, this is going to be a more of a general access machine so that anyone here with Department of Energy, Office of Science funding can apply for time on this machine. There's no requirement to do hero calculations. And so here we have a general access, very powerful hybrid computer. And of course, next year we have the exascale machines arriving, Aurora at Argonne, which is going to have Intel Z GPUs and Xeon CPUs. And then at Oak Ridge, the Frontier machine, which has got AMD GPUs on it and AMD CPUs. All this information is from these public websites. And of course, our challenge as essentially sort of developers and maintainers of the code is that we need to make sure that we can run on everything from a student laptop to a departmental cluster through to these machines, which have actually got GPUs from 3 different vendors on them. One thing, of course, I want to note here, of course, that we should always take care about this as scientists, is that as we have new resources made available to us, actually, as Eric was pointing out, we should take care to see if we can use this computational power to use new methods, not just the ones we've been using so far. And so that brings me to the method that we're focusing on here, that of quantum Monte Carlo. And I'd like to thank Professor Philippi for touching on this last week. They're working on this in the context of the TREX Center for Exascale Chemistry Applications. And our funding is focused on materials. What's special about these methods is that we're solving Schrodinger's equation stochastically. So to compute materials properties, the rules of the road are given by quantum mechanics. So we need to solve the equations of quantum mechanics. And one thing that's very attractive about these methods is that there's not many approximations made in them, and we actually know what they are, and you can potentially test them. And so that makes them quite different from many of the other theories that are out there. There's a range of methods, and QMCPAC has traditionally mainly had real space methods in there, but we've recently added the auxiliary field quantum Monte Carlo method, and these behave very differently. Auxiliary field is much closer to a quantum chemical or basis set method in behavior. And there are also other methods that I'm not going to touch on today. This is a quick talk, such as full CI quantum Monte Carlo. But I'd point out there's actually a very nice talk by Professor Ali Alavi on the CCAM YouTube channel from last year. So you could go back and watch that. As Professor Philippi pointed out last week, and I also want to reiterate, these methods are not exact, at least as you normally run them. But they are very accurate today, and there's some fundamental reasons why this is the case. They scale well, and importantly for us, they do the physics that we're after. So for example, you can apply them to metallic conductive systems as well as insulating systems. As I think a lot of the audience probably knows, there's a very famous challenge in doing these computations, and that is the so-called fermion sign problem, or accounting for the symmetries of the electronic wave functions. In the real space methods, this is usually solved by something called the fixed node approximation, and what that does, it introduces a variational error in the energy. So you have to input some kind of guess wave function, a sophisticated guess, of course, and this energy you get is going to be above the true ground state energy. And then if you put in a better guess, you'll get a lower energy. So this actually allows you to test your inputs and set up an optimization scheme. I would point out, of course, we're doing Monte Carlo here, so all the things we learned about in our first numerics course apply. For example, we converge with the square root of the number of samples. We're developing the QMCPAC code, as I've pointed out. So fully open source, we openly developed this, aiming for very high performance in the methods that I've mentioned. If anyone is interested, I'd suggest just to type QMCPAC into Google Scholar, because we recently wrote a review paper, and actually it's in an edition of the Journal of Chemical Physics, which is, there's a special topic on electronic structure codes. There's lots of interesting papers in that are well worth looking at. And then also a few years ago, we wrote a citation paper. And one thing that was interesting is that our code has always been under version control. So we were actually able to go back and see who has touched and contributed to the code. And we got up to 48. So this really takes a long-term sustained effort. And of course, we do lots of activities. And of course, the one thing we miss at the minute is annual workshops. We get a lot of feedback from our users there. So what can we do with these methods today? What I want to do is show a couple of quick examples, two from the Reberido group at Oak Ridge, who are users of QMCPAC, and then two others from the literature. And I've tried to pick some that are not hero calculations and are sort of representative of what one can do today without ridiculously large resource utilization. And so here for the experts, you can read the text, but for everyone else, I'm just going to talk through this figure. So scandium oxide is a material that exists in several different crystal structures. And the basic question is, can we get the ordering and energy of those crystal structures correct? And the results are here. So diffusion Monte Carlo is this red line. It's got its error bar on it. And fortunately for this material, we have experimental calorimetry. We don't always have that for the all materials, of course. So we would like more of that work to be done. And we see happily that we're in good agreement. This also applies for the other crystal structures. And when we look at a zoo of other cheaper methods, we see that we don't find ones that actually match. And of course, this is unfortunate because we want to look at more complex materials, more complex behaviors with these methods. And this is actually an area where, of course, we would like to see more improvement. So the existing methods work accurately in that case. Here's another example. This is actually looking at the light emitted by a material. So we're using manganese to dope a number of materials. And the basic question is, what color is the light? So here's the energy of emission, and the green is experiment, here. And here is actually a prediction where there's no experiment. So it says actually we should have red emission in this material. So this was about 1 million CPU hours, which is certainly not nothing, but it's not, that's actually very gettable these days. So again, quite good agreement with the existing methods that we have, although of course they're still approximations, and I'm going to get to that in a moment. Two other examples from the literature, this by Chiba in the Maizeno group, looking at titanium interstitials in titania and how that might affect catalytic activity. And here's an example on the right, a molecular calculation. We can also run chemical calculations, looking at the structural distortion in carbon rings, which is a very famous problem in quantum Monte Carlo. So what are we excited about moving forward as we get more computer power? Well, most definitely in this first point, we are in a growth phase where as the computer power increases, we can definitely do more complex materials and importantly, using more elements from across the periodic table. Because in our method, we pay by the electron count. So we care about the electrons. But there's also a number of other things that we need to be able to do and want to be able to do that require fundamental methodological improvement. And so, for example, tackling the fermion sign problem, which is the method approximation I mentioned earlier, putting in more physics. And then importantly, making better connection from our so-called quantum many-body calculations to measurements that can be done experimentally. You'll notice that I showed energies so far, and it's very rare actually that you measure energies experimentally. And importantly, we have this whole ecosystem of different theoretical methods, and we want to make better formal connection to them. So these are all areas where we need to do some fundamental theory in addition to using the increased computational power. So I'm just going to show a couple of examples moving in that direction to show that there's real promise here. So here's a couple of two projects. These are both submitted and under review. Where are we moving towards a theory which is internally consistent or is only very weakly dependent upon a starting point? And that would be a big advance, because that will let us look at the most challenging materials and the most challenging physics, which is difficult to do today. Of course, doing this is going to require a lot more computer power, but we're also going to have to use some smarter mathematics and insights for the functional forms we use in our wave functions. So let me talk through this first project. This is antiferromagnetic iron oxide, very challenging material to look at. And what we've done is done so-called orbital optimization, change the orbitals that make up our input gas, and optimize them fully within the quantum Monte Carlo. And I'm showing here results for the cheaper variational Monte Carlo method and then the more accurate diffusion Monte Carlo method, which gives lower energies. And here are two different starting points. And what we see here is that we get very close to the same result for those two different starting points after this procedure. And then also strikingly in this case, we actually get the lowest energies, so the best results, we know that formally, doing this procedure. So this is a big step towards having a theory which is independent of the starting point, and happily, at least for this material, it's actually got the most accurate results of all the sources of trial wave function that we had so far. Of course, we want to now do this in more general materials, which is going to require a lot more development in new theory. And then here on the right, I'm showing a cross-validation between two of the methods that I mentioned, auxiliary field and diffusion Monte Carlo. Because as we have these implemented equivalently in the code, we can now have a sort of a race or a friendly sort of competition to understand their behavior and learn how we can improve one based on the performance of another. So for example, and this is done in a small primitive cell, so this is not fully converged, but it's small enough that we can brute force the exact answer, which is this dotted line here. And for example, we see that auxiliary field here in lithium fluoride bulk is strongly basis set dependent, but if you do all the extrapolation, you converge to the exact answer here. Whereas the longer established real space diffusion Monte Carlo, it starts off more accurate, that's these solid bars. And then when we try and improve the wave functions, with multi-determinant wave functions, more sophisticated, more parameterized wave functions, we actually have to work quite a lot to improve them. And we don't quite get there in this lithium fluoride case. And we have a long way to go even in carbon diamond. So now, because we have cross-validation, this is going to motivate us to try and improve the diffusion Monte Carlo here with smarter choices for how we improve the wave function. And again, we want to bring this to more complex materials from elements across the periodic table. I mentioned connections with other theories, and here's an example that was published last year. We want to be able to predict optical properties, and famously, quantum Monte Carlo normally does this one state at a time, which is making it very expensive to look at the whole optical spectra of a material, where there's other methods such as W, which will give you the whole spectra. So we'd like to connect them. And in this paper, a very simple ansatz was used for the wave function, and instead of trying to converge individual calculations, what was done was to try and arrange for good error cancellation between ground and excited states. And this actually worked really very well for this range of materials in actually a simple quantum Monte Carlo method. So this actually wasn't even very expensive to run. We didn't use a great deal of computer time to do this. And one thing that was very interesting then was that, well, we actually have the wave functions for these states in this method. So we can analyze them, and we ran zinc oxide, and we were able to understand some of the sensitivities in other methods, which we then, of course, then use to compute a whole spectra. So that's an example of linking two different theories that we want to do more of in future. So a quick summary, having gone through the sort of quantum Monte Carlo part, I hope I've shown you that these are highly accurate today. And importantly, we're now able to make some progress testing the few approximations that we have in them. But there's still a lot of fundamental improvements that we need to do. So now let's talk about the computational situation. So I'm going to broaden out now to more general comments. So I showed this list of some of the upcoming machines we have here. And of course, there's going to be a lot of challenge in running on them. So I wanted to make a few general comments in the spirit of being H.P.C. Earnest, which is the title of this series. So this is fortunately touched upon in the last talk, but there are some very serious challenges here. So of course, we have to respect Amdahl's law, both in parallel scalability, and this is something that we have to work a little bit at in quantum Monte Carlo. So it's not trivial, but we can do it more easily than many other methods. But then, of course, if all these machines have accelerators on it, or perhaps our CPU has got specialized vector processing on it that we need to make sure we fully utilize, our maximum speed up is going to be limited by the amount of the algorithm that is not running efficiently on the accelerators. We, of course, have to manage memory and data movement very, very carefully, which is one of the more costly operations that we do. And one thing that I really want to stress that was touched upon by Eric in his talk is really just how massive these accelerators are. Whatever the future is actually going to be, is always going to be very massive with a huge number of compute elements. So just to keep, even actually, well, this is now a previous generation GPU occupied, you need tens of thousands of floating point operations executing at once, preferably orders of magnitude more than that, all going through the pipelines to be able to run efficiently and keep the card occupied. And so this is a lot of work. And for our quantum Monte Carlo, we don't want to just speed up the very largest calculations with a huge number of atoms and electrons. There are lots of important scientific problems that don't have many atoms and not many electrons, and we also need to speed those up. So we can't just rely on doing a quote unquote big calculation. And so what was worked out a few years ago, at least for Monte Carlo, was that you can essentially group operations over multiple Markov chains. And that helps us get the additional work. Obviously, there's lots more I could say here, but these are really important issues. What have been helpful strategies for us is to have a hierarchy of different pieces of code. So we have standalone kernels, so individual operations that people can work on. We've developed a QMCPack mini app, which is a heavily cut down and simplified version, as well as also the full application. And the idea behind doing this is that it helps in analysis, it's much easier to do experimentation, and it's also much easier for a non-specialist to engage with either the mini app or the kernels, right? They don't have to learn all of our jargon about electrons and wave functions and the soup of quantum Monte Carlo methods. As an example of some new algorithms and also some new efficiencies that can be enabled or might be required, let me show two projects here. So first, one of the more costly elements of a real space quantum Monte Carlo calculation is when you move an electron, we have to update the inverse of a determinant. And that actually runs very efficiently, not only inefficiently, that runs inefficiently both on CPUs and GPUs. And so what we did a few years ago was to realize that we could delay making these updates and compute an iterative correction for a few moves, and then do a larger update, using matrix multiplies, which works more efficiently. And so this is actually a result on a CPU system. And if we look here at this curve, this actually is the overall speed up in the diffusion Monte Carlo. And this is with 1500 electrons. And we see it's maybe 3 times faster than without this algorithm. So that's the big improvement. Of course, if you only have 100 electrons, this algorithm doesn't help you so much. So other tricks are needed. And then here on the right, this is an example of an algorithm which is now surprisingly efficient on the GPUs. And I think it's going to be a real sweet spot for this methodology. So we have a new implementation of auxiliary field quantum Monte Carlo that can exploit essentially k-point symmetries and sparsity in the Hamiltonian. And when mapped onto the GPUs, we see this is the essentially the performance. This is the new implementation here. And we compare it against the same implementation running on CPUs. We see not only is it much faster, so lower is better on this curve, but actually the speed up increases with system size. And that's because we're enjoying the memory bandwidth on the GPUs for some of the important operations. So bulk calculations is going to be a real sweet spot, I think, for this theory. So now I'd like to broaden out before wrapping up the talk. I want to make an important, sort of general recommendation. So if we think about, what are our challenges and where we are now, well, we know that our science is quite complicated. It takes many years to make significant progress. And as a result, all the codes we're developing, they're around for a long time, perhaps decades. We know that computational hardware is evolving and diversifying. The languages and software tools are also developing at the same time. And generally, what I see here is that complexity overall is increasing. So if it was ever possible for one or a few people to keep track of all these things, which I would actually question, it's becoming much less so today. So effective collaboration is becoming even more important. And I don't just mean within our subject areas, I mean with computational scientists, software engineers, and so on. So my one large general recommendation, which also touches on the previous talk, would be, if you're a student thinking of developing a code in the listening, to spend some good time thinking about the design of your software and how you can improve the accessibility of this software to non-specialists. So how you can get some support from perhaps support engineers at supercomputer centers, maybe the vendors themselves, mathematicians, or just an open source contributor somewhere out there on the internet. What do I mean by this, and what would the ramifications be? Well, I think we've all seen or drawn a sort of an application like this, where we have sort of a user interface. We have our domain algorithm. So this is where we do our quantum Monte Carlo. Most methods have some special numerics that are distinct from what other algorithms might have. And then at the bottom, we have our vendor libraries and vendor-specific code, because we still want to take full advantage of whatever special features any one vendor has. But what we want to do is push up abstractions as high as we can for generic algorithms, and push down the specifics. So try and avoid having vendor-specific code up here. And then what are the ramifications of this? Well, I've made up an example here. If we have a hypergradient that we need to compute, well, we've already written a unit test, and if we want to optimize it here on ARM, we can hand this over to a specialist who now only needs to go through our specialized numerics. They don't need to know anything about our problem domain. So it's going to be much faster for them to get up to speed and make a contribution. And then, of course, the same thing would apply if we did here. I made an example of NVIDIA. And I think the codes that do the best job of this are going to be in by far the best stead for the future, simply because of the increasing complexity. So now to wrap up, I'd like to conclude. I hope I've shown you with some of the promise of quantum Monte Carlo is going to open up some new methods and hopefully new scientific applications. But I would also caution about the increasing complexity, both in the diversity of the hardware and software that we're going to have to use, and encourage really a considered approach to using this. Thank you.
Thank you very much, Paul. to all the speakers that we've had today. So now it's time for some questions and answers. We haven't got that many questions on the chat yet. So we have one technical question for Paul. I will start with that. But since I think that we can have a very interesting discussion also through interchanges between our speakers and ourselves, I would like also to invite you all to think, Eric and Jesus and Ignacio, to think about things that you would like to ask each other. So the technical question for Paul is, can quantum Monte Carlo take into account vibrations, and in particular take into account things like Helmholtz free energy and vibrational contributions?
This is a very important question, actually. And one of my earlier slides, I wrote phonons. Because also, of course, at Oak Ridge National Lab, we have the spallation neutron source. Obviously, we'd like to make connection with that. And this is actually very challenging because it's dealing with essentially the gradients of the energies to get to vibrational properties. So I would say it's a research topic. I believe Professor Philippi might have shown some forces and relaxation in her talk, but this is still not very widely done in materials. And that is, we need to get to forces in order to be able to start getting free energies and, of course, moving atoms around. And this is actually an area where I think making connections to other methods is going to be very important, because if we could show, oh yes, this DFT approximation is really good for this material, then you should just go off and use the properties that you get from that DFT approximation, or perhaps we can optimize one in some way. So we want to use the methods where they're at their strongest.
This is just to get a feeling, Paul. How would you estimate, what is the difference in cost between, say, trying to accomplish one MD step using QMC as the origin of the forces and DFT?
This is a good question, and the key, but it's actually not really a question that's possible to answer without knowing how accurately you need those forces. So, for example, a number of years ago, it was shown that you can run bulk water and get good properties with quite large stochastic errors on the forces. So if you can arrange a sampling scheme that can cope with stochastic error like that, then it's going to be much cheaper than if you naively use a conventional steepest descent numerical method to optimize geometries, for example. So this is actually one area where a lot of research is needed. And of course, it's something that we are looking at.
Okay, thank you. So do we have questions from any of our other speakers, or Paul, if you have a question for someone?
I'd like to throw a question to Eric, actually. So I have a lot of projects involving electrochemistry. So this is an area for energy storage. So this is an area where we have water usually, or ionic liquid, we have ions, and we also have electrons. So we have some reactivity. And this is something that's not normally included in classical dynamics. And I hear it talked about a lot. Is this something that they're considering, and would it change their computational approach at all? So to add a reactive force field?
Yes and no. So there are two parts of this. An easy way to do it is in general to do QMM style calculations. The advantage of QMM is that it works well. So you designate, assuming that there is a particular bond that is likely to break, or a proton that's likely to change. It's easy to define, reasonably easy at least to define it. The physics works. We understand the physics really well. Now, the cost of all this is that you're now doing QM for a large part of your system. And no matter the amount of buzzwords people use about multi-scale models and everything, that also means that you get the resolution of QM, but you're also stuck at the timescales of QM. So you're never going to get millisecond simulations of QM, right? And that's the hard part there. So if electrochemistry in general is a harder problem, but a very simple problem, if you talk about protonation, then we can cheat, because in that case, both the end states are well defined. And then you can essentially use lambda dynamics, where we turn the proton itself into a lambda parameter with between 0 and 100% occupancy. And it's kind of the same thing as with classical simulation, right? It's a horrible approximation of the underlying physics, but the end result works well, because at the end, we're only going to predict the end states. is if I needed to sample things in milliseconds with any type of reactivity, I would likely try to find an approach like that. Can I cheat a bit so that I'm not forced to sample all the quantum chemistry of the entire process? Because then you're going to be stuck with nanoseconds, at least for now. Now, on the other hand, the good part here is that the QM can occasionally scale really well on some of these large resources. So one approach that we recently tried to think more of is that rather than seeing this as a curse that we don't have enough floating point operations to saturate all these processors, maybe we should start to see this as an advantage. Suddenly we have more floating point operations to spare than ever. So that probably means that it's time to revisit all these algorithms that we used to think that they were too expensive because they use too many floating point operations. In the vast majority of cases, I think floating point operations are no longer going to be the bottleneck. So we should stop seeing them as that. But it's hard to rethink.
It's not just hard to rethink within a specific code. I think it's also interesting, and this is another example of the need for more collaboration and talk between different communities, because someone like Harry talking to someone like Paul, or talking to someone like, I don't know, the developers of QMMM intensive codes, or that have that potentiality like CP2K or other things like that. I think it's very, very important to try to foster that kind of discussion. Not to reinvent the wheel every time, but to allow different codes to talk to one another.
No, indeed. And I would say that sadly, it's only now that we're finally learning from all these QM codes. We used to think that they were so stupid for recalculating things instead of storing it. But that, of course, was because they were more memory sensitive. And we had never before, nobody doing classical MD ever bothered about memory. You would always buy the cheapest memory you could find. And suddenly we too are becoming memory limited, and recomputing things is starting to look a whole lot more attractive than it historically did.
Is it possible, now I'm going back to the chat, there is another question directed at Paul, but I guess it's, is it possible to have this different level of resolution also in QMC type of schemes? I mean, do you need, in a quantum Monte Carlo calculation, do you need to treat all particles at a quantum Monte Carlo level, or could you embed QMC within less exact theories?
This is a good question, and I think our recommendation and experience is going to follow what's been found in the world of quantum chemistry. So yes, if an embedding approach makes sense for your problem, where you can treat some region quantum mechanically and then do a larger region, you might do that. And there's certainly a few papers in the area, but it's not widely used because you now have an interface region, right, which can have quite long range effects. And so you have to be very careful that you have a sufficiently large region that's going to have the accuracy you need for the quantum mechanics. So I think inevitably there's going to be some of this utilized, but it's very difficult to use in practice.
But this is the same kind of difficulty that you find in QMM calculations. So when you have DFT embedded in classical matrices, or there are additional technical difficulties?
To be brief, it's no better.
Okay.
Very similar.
I actually had a question for Jesus, now sort of zooming out and going a bit more in the direction of good practices for code development. And that is, what is your impression in this discussion that is taking place now in between the idea of having modular developments for software, libraries that can be adapted to different codes, that can enhance functionalities in an integrated way, versus the idea of having, more monolithic type of things that are dedicated to specific applications? Do you have any impressions about the pros and cons of the two approaches from a performance analysis point of view?
Well, I would say from the performance analysis point of view, there is no real difference. We can look at whatever you use. I mean, for people, if they have libraries that might make the problem, and it was mentioned by Paul about this decoupling between. So I was advocating for this osmotic membrane between hardware and software. And I understood he said in terms of also a osmotic membrane between different layers in the software. And I think this is a good thing. This is something that not everybody, we all believe that our library is more specific and is better for our kind of problem. So this is something that is going always to be there. And it has to be for the application developers to decide what is going to cost them less effort. What certainly happens in POP, for example, is we are analyzing codes where we end up finding that the major issue is in the library they are using. And by the way, the library is not developed by them, but it's a standard well-established on the other side. It's a well-established library, but we find the issues there. So the issues can be everywhere. What I think is important is these osmotic membranes between layers, the interoperability, how they interoperate, how they work together, and how one level can steer the one below, and vice versa. Follow the level on top, follow the indications for the one below, Yeah. In a sense, for example, and this may be a question, I don't know, Eric mentioned Fugaku, okay? And I don't know what you all think, or both of you think about the vector length agnostic type of features or capabilities, these things where actually the programmer says, I would like these long vectors, and the system decides, well, in reality, I am an implementation with this many bits only, so you will be doing in pieces. So I think this is a kind of negotiation that actually even happens between programs and architecture at that level. So from my point of view, I think these kind of things are important. So going to your point, they are important in the architectural point of view. So between the ISA, let's say, and the microarchitecture, they are important between the programming model and the runtime. And I think they are important between the different layers of algorithmic libraries or application level libraries.
Mm-hmm.
So I can comment briefly on that. So one of these vector length agnostic architectures now is ARM provides some pretty awesome tools for this with the new scalable vector extensions of Fugaku. So that basically, there is of course a vector length to the hardware, right? But the way you write the instructions, you pretty much formulate this as a loop, and then the processor itself will express this in vector instructions. I think this is tremendous and awesome for general to be able to vectorize general code automatically. Now, the challenge, if you remember the algorithms I spoke about, the challenge for the algorithm is usually that the best vectorization for most scientific algorithm is to not vectorize at all, but to treat things in 1x1 units. That's going to maximize the number of the efficiency for us. So anytime I'm moving to larger tiles or vectors, so that I accept that my efficiency is decreasing in order to be able to saturate the hardware better. But that of course means I only want to go as far as absolutely required for this hardware, because I don't want to pay extra to have a gigantic cluster size that will work on any hardware. That's going to be suboptimal on all the other hardware. And this might be particular to our algorithms, but possibly also matrix. Well, matrix multiplications is another part, right? You frequently want to optimize the tile sizes to the cache and everything. So I guess it depends a little bit on what one's doing. If you want a general, fully portable code, then I think it's awesome. If you really want to use the hardware to the fullest, I think there are things in the hardware that will influence what algorithmic choices you make. For instance, if you know that your memory is slow or you have complicated new architectures, that might be something you have to take into account for your algorithm. So in general, I don't believe in fully hiding the hardware from the user. Or rather, you can do it, but you will be paying a performance price for it.
No, and we can have explicit so some different point of views here. Yeah, but in a sense, for example, you actually mentioned, for example, some of the refactorings that you have done for GPUs, then go back to CPUs, and then you get better. And my point is, to what extent isn't that because with the GPU you were forced to think of that, and you found out and you came out with some fundamentals that are fundamental. They are not specific to GPU. They're not specific. They can benefit everywhere. They're fundamentals. And the question is, if we're able to get to some of those fundamentals and we are going to express things in terms of those fundamental things, I think we should get to encodings, to programs which are really closer to the kind of view that I'm trying to defend, and I understand, and you have been doing great work in terms of really optimizing for specific things. I agree on that.
Yeah, but I agree with that. The abstraction is important, and it's going to be so difficult to handle all these pieces of hardware and accelerators that we need to abstract, if nothing else, because we don't have enough manpower otherwise.
Yeah.
I have a curiosity. I mean, Eric, you were showing this extrapolation in the number of cores and how it will increase in the future. If I understood correctly, you, at least for MD, you were saying that at some point it really doesn't pay off going to larger and larger systems, and then it's the time evolution which becomes eventually the bottleneck. I think you were more saying that then you need to move.
I would say for MD, this has happened already. I think for a whole lot of other fields, it's going to happen. So I know less about quantum, but one good example, or it's good because it's bad, it's fluid dynamics. We've always been jealous of fluid dynamics, because fluid dynamics, they have this thing that if they're modeling flow over an airplane wing or something, right, and they can always make their model better by moving to a finer mesh. And if they just have smaller grid cells, that suddenly that means that their problem is 1 million times larger, and then they can use 1 million times more nodes. So their scaling has always been tremendous. Now, the problem with that is, of course, for them too, at some point they will hit the wall where sure, they can increase the mesh, but it's not really improving their predictions anymore. And that is likely bound to happen within a few years for computational fluid dynamics too. And then they too will be in the point that weak scaling is not going to work for them. They need strong scaling. And I think there are very few. I can't immediately think of any algorithm that's going to scale trivially to an exascale machine, unless it's a stunt problem just made to scale. But the vast majority of scientific algorithms where you first try to reduce the size of your system will have problems scaling to them.
Wave function propagation.
Yeah, but will you be able to scale it efficiently to 1 billion cores? Because you're going to have communication bottlenecks and everything. So it's one thing that we would like to use all the floating point units. So would I. But then we have the communication latency and everything. That means that in practice it's not going to work.
Again, I was just thinking that maybe we can.
I hope I'm wrong.
No, I was just thinking that maybe we can learn something from the mesh people in that domain and try to scale better in that type of calculations. So we have a couple of new questions from our audience here. First one is for Jesus. Actually, it's the second one, but I'll ask that one first. Do the results from POP feedback in a meaningful way to the relevant standards committee, for example, OpenMP, OpenACC, or to vendors of compilers and libraries? Do you have a dialogue with them?
We try to do so, yes. We have, we participate in the standards bodies, particularly in OpenMP. There's several partners. VS is in Boulder, but Gen is also in Boulder, so we are active on that. We are working on open source implementations on some of the ideas that we try to develop. So I would say certainly yes. But we also have cooperations. We have cooperations with with Fujitsu, for example. We have our OMS kind of system running on the Fugaku. Okay, so this kind of things we try to push them. It's always a very slow feature. It's always there's this saying, against the vice of asking, there's the virtue of not giving. I don't know if the translation, but I mean, you can propose things, but the standard committees have their life. But my experience has been very positive in that we try to propose things that we believe are the most appropriate. We try to push them. Some of them make it, some of them don't, but we try to follow have an impact, yes.
Thank you. Then the next question is for Eric, and is more technical here. So even with the biggest computer and best possible codes, can force field-based simulations be predictive for drug design? Shouldn't the chemical bond breaking here limit the scope?
Oh, there were a lot of different questions. First, for drug design, there are very few cases where you make or break bonds. I can't immediately think of anything. There are no drugs that would be covalently bound, because if the drugs were covalently bound, the molecule would never ever leave your bloodstream, and that's likely very bad. And the same, so I would argue it's the same thing as when it comes to protein folding or so. It's actually very rare in your body to make or break bonds. I guess the synthesis of amino acids is one exception, but that requires an enzyme. So I would say, yes, they are predictive, but it's also, drug design is a very special thing, and that's actually where docking comes into. So for drug design, the main goal is not to achieve perfect predictability, but rather to achieve very high throughput, and in particular be able to get fast predictions of molecules that are, for instance, difficult to synthesize. And this is an area where both MD simulations and docking are already used. So it's not hard to synthesize a molecule and go in and test it in the lab. The problem is that it might cost you $50,000 for one molecule, and it might take you 6 weeks. And if you would now like to do this for 100,000 molecules, you'd better have a very big wallet. So the MD simulations, they might suck. The question is, do they suck so much that it's completely random? No, they don't. So assuming that we have COVID-19 right now, and there are of course drugs, but the goal is not to find the theoretically best possible inhibitor of the SARS-CoV-2 virus. We just need to find one inhibitor. And if it's not the best, too bad, but it's an inhibitor. And that's usually the approach people take. So we rather use both docking and molecular simulations as the rapid screening stages to find the ideas quicker. Once you have a few leads, we much more systematically go into the lab and try to add or remove functional groups and also test them experimentally. But it's important that I would never ever take a drug that was based entirely on computational predictors. You do need the experiment to validate it.
Thank you, Eric. Ignacio, do you?
I mean, building maybe on what, so I had a couple of questions. One was for Paul, because you were talking about taking advantage of the landscape of methods, and now in the H.P.C have to rethink about them. So how do you see that evolving? Do you think that there is one of these algorithms or approaches that is more promising, either because of how it scales or because of its fundamental, how it's the foundations? Or when you talk about the ecosystem, you mean that you need to have a number of them sort of like combined together?
So in a general science investigation, we are going to end up doing some quantum calculations, some classical dynamics, and we might even get rid of the atoms altogether. We could even do some phase field, for example. So we're naturally going to be using a range of methods. To do more than simple parameter parsing, we need to do the fundamental work to match up the parts of the theories that are common between them, for example. So for example, the electron density in density functional theory is the same electron density that we can compute in quantum chemistry and the same electron density that we can compute in quantum Monte Carlo. The response of the system should also be the same. So there are various terms in different theories that we know should be the same, and you could potentially join methods this way. And of course, these days, we haven't spoken about data-intensive methods, but there's of course the worlds of machine learning and AI, which might help us in doing some of that stitching of theories together and upscaling in a more sophisticated way than we're doing today, or perhaps just a more scalable way that's not so human dependent on what's been done in the past.
Mm-hmm. Okay. I don't know if you have questions. There is one I cannot resist not making to Eric, because Eric has started his presentation referring to this famous 1976 workshop that actually took place in CCAM, and that in a way opened this new way of looking or start thinking about proteins and how that changed modeling and our understanding of these systems. I don't know if now with this, we have been talking about this landscape and what is expecting us and how this is changing the way in which we look at modeling and simulation. Would you dare say, what do you think this may change qualitatively in how we see or understand this biochemistry or biophysical systems?
Ooh. I think it has changed. It has changed tremendously. And I would actually, I think there were some ways we went wrong, if I put my physicist hat on me. I think for a long time, I think physicists and modelers came into this with the attitude that simulations had somehow replaced experiments. And this is also where we cared so deeply about the strong predictability, right? And I think that we've mostly given up. And I think it's a very good thing that we've given up on that, because what's happened is that simulations are increasingly treated just like any other experimental method. And that's, we kind of trust it, but we also know that they are black boxes and there are lots of things that can go wrong, and no biochemist would ever believe one single method completely. So I would actually say that it's a sign of maturity that we don't necessarily trust everything in simulations. And if anything, I'm occasionally worried that we trust them too much. So I can make an analogy here that with cryo-EM that we're doing a lot of nowadays. So is cryo-EM an experimental or computational method? I think the vast majority of people would say that it's an experimental method. But if you look at the work, it's, of course, it's a tremendous amount of work purifying and overexpressing protein. But once you put them in the microscope, it's roughly an hour of work of freezing the grid and putting it in the microscope. And after that, all the work is computational. So the model building is computational, and yet we don't really think of it as a computational method. So I think we're kind of blurring the entire boundary between computation and experiment. So that's probably the part that I find most exciting, rather than computations displacing or replacing experiments.
Mm-hmm.
So that what that has led to in biochemistry in general and structural biology in particular is that even experimental teams, and we're one nowadays, think of structures much more as ensembles of structures, collections of structures, all these things that come very natural to a physicist, right? That we talk about free energies, relative differences in free energies. And suddenly experimentalists started talking about that too. And I think it's a greater impact than I could ever have dreamt of. So 20 years ago, my goal was that we should have experimentalists trust our models. And I think what they do now, they not only trust our models, they've adopted our entire language of talking about structures. And I think we can't wish for more.
Okay, thank you. I don't know if you have any additional question or comment you want to bring in. We have been discussing now for almost half an hour. So
No, we could open a bit of a philosophical discussion, because not only is the boundary between computation and experiment blurred, right? But what we call theory and computation and experiment, it's also, I think, an evolving scenario. But maybe this is for another series of webinars, no?
yeah.
So no, I think.
Okay, I think it's a good point to close it, probably, in this note. So thank you again to the three speakers for these very engaging presentations and for the overall broad discussion. I hope that all people attending this session will have enjoyed and will learn about it. And I hope to see you again. We'll have the third session of this webinar series next Thursday. So see you again in a week. Thank you very much. Bye.
Thank you. Bye.
Bye.
Okay.